Let's say you have two vectors and want to know the angle between them, but you forgot your protractor. What do? Welcome to but one application of the dot product. To perform the dot product, we simply multiply two vectors component-wise and then add the results. Say vector A is 1, 2, and vector B is 4, 5. Then the dot product of A and B is just a sum of 1 times 4 plus 2 times 5, which is 14. Or in 4 dimensions, if A is 0, negative 1, 2, 3, and B is 1, 0, 5, negative 2, then A dot B is 0 times 1 plus negative 1 times 0 plus 2 times 5 plus 3 times negative 2. Which once you sum that all up is 4. Note that from this definition of the dot product, the magnitude of A is intimately linked with this dot product. Since the magnitude of A equals the square root of A1 squared plus A2 squared plus A3 squared and so on, that actually equals the square root of A1 times A1 plus A2 times A2 and so on for the rest of the vector components. But then realize that A1 times A1 plus A2 times A2 and so on is really just the dot product of A with itself. So that gives us that the magnitude of A equals the square root of A dot A. And note that A dot B is 0 if and only if A is orthogonal to B. For example, if A is 1, 0 and B is 0, 1, they're clearly orthogonal, and as you take their dot product, you have 1 times 0 plus 0 times 1, which is 0. Now I want you to follow me on a quick journey for a moment while we see what we can learn about the dot product by playing with the law of cosines for an arbitrary triangle A, B, and C. I'm going to print this since writing it might get jumbled and I have bad handwriting as it is. Recall that the law of cosines states that c squared equals a squared plus b squared minus 2ab cosine of theta. And in this equation, a squared, because it's the length of one of the sides, is actually just a dot product of, for example, a with itself, a. And because we know that c is just a minus b in this triangle, we can plug a minus b into c for this equation, which gives us a minus b squared equals the right side of the previous equation. And as we multiply this out, it gives us a squared minus 2a dot b plus b squared equals the right side of the equation. Remember that we got this a dot b because we're multiplying component-wise. Just like a squared is a dot a times b is a dot b in this situation. So from this, we can subtract a squared and b squared from both sides of the equation, which leaves us with minus 2a dot b equals minus 2 times the magnitude of a times the magnitude of b cosine of theta. And by dividing both sides of the equation by negative 2, we get our final equation, a dot b equals a times b times cosine of theta. Now, using this equation, we can solve for the value theta between two vectors by dividing both sides of the equation by the magnitude of a times the magnitude of b, and then taking the arc cosine of both sides. So if we are given vectors a and b, we can easily calculate the angle theta between them. If a and b are orthogonal, then the angle between them is pi over 2. So if we plug this into our equation that we just derived, we have that the dot product of a and b is the magnitude of a times the magnitude of b times the cosine of pi over 2. And since the cosine of pi over 2 is 0, we find that the dot product of a and b is indeed 0. Another use of this formula is in solving the projection of vector a onto vector b, which is a cosine of theta. We can solve for this by dividing both sides of the equation that we found before by the magnitude of b. That gives us the projection of vector a onto vector b, like you can see in the diagram. The dot product follows the commutative and distributive properties. The commutative property states that a dot b is equal to b dot a. The distributive property over addition shows that a times the sum of b plus c equals A dot B plus A dot C. To conclude, the dot product can be used in a large number of ways. We drew the formula out of the law of cosines and then used it to solve for an angle theta between the vectors and how to find the projection of one vector onto another.